Hi all. So today in my video, the first information I wanted to tell you that I will be taking classes in English so that it will be helpful for more people. Right. So without much delay, I am going to the topic. We are discussing on some of the basic things of organic chemistry, and I am referring Clayton for all those things. In the last class, I discussed on how a bond is forming in organic chemistry, who is attacking, and in which center it is attacking. All those things I discussed in the last class was basically on bond formation, nucleophile, and electrophile. I will just revise that so it will be helpful for the new viewers. So in 5 minutes, in the first 5 minutes, I will be discussing what I already taught in the last class. So already who watched those things, they can skip this video. Okay, so basically, how a bond is forming in organic chemistry. Like A plus. So just consider this is A plus and this is B minus. Such kind of electrostatic interactions, such kind of electrostatic attractions are not that common in organic chemistry because there is very few stable ions in organic chemistry. So that such kind of A plus plus B minus, such kind of reactions are very less. Instead of that, the reaction is between a charged reagent. A charged reagent means, example, we can take a Cn minus. This is Cn minus, take it as a Cn minus, and there will be a dipole. Dipole means C double bond O. We all know, because it's a very common functional group in organic chemistry. It can be seen in aldehyde, ketones, carboxylic acid, anhydrides, everywhere this C double bond O is there. So because of the electronegativity of oxygen atoms, there will be a polarity. There will be a dipole. Because some positive charge will be there at carbon center and some negative charge will be there at the oxygen center. So such kind of dipole and a charged reagent can interact and thus a bond can form. So in that particular positive center, the Cn minus is a charged reagent. So they will attack and such a way this bond can form. Also, if there is no this kind of charged reagent, also, for example, take the case of NH3. NH3 has no charge. Take the case of BF3, that also has no charge. But even though they are interacting, because they are interacting through their molecular orbitals. One has a filled orbital and other has an unfilled orbital. Another has an empty orbital. So by the interaction between this filled orbital and empty orbitals, they are interacting. So it is not mandatory that there should be some charged interactions or such kind of thing. So our key point is that, so while writing the mechanism or while choosing like how the product is forming, the important thing is that we should choose the nucleophile and electrophile very carefully. Then it is very easy to write any mechanism in. There is no need of studying all those named reactions. It is important to study named reaction, but even though we don't know, we can write it as our own. Because we know who will attack, in which center it will attack, which is the best nucleophile, which is the best electrophile. If these basic things are clear, organic chemistry is very easy. It's the most easiest thing in chemistry, I can say. Okay, so which is the best nucleophile? This PDF I will upload, but I'm just revising for all of your knowledge. Okay, so which is the best nucleophile? Best nucleophile is that which has high energy occupied molecular orbitals. HOMO, we'll say HOMO. So which is the best electrophile? It is the lowest energy unoccupied molecular orbital. So that this high energy occupied molecular orbital can interact with low energy unoccupied molecular orbitals. This is how the interaction is happening. So the key concept in organic chemistry is that the electron is moving from the nucleophile to the electrophile. This is the key of mechanism of any of the reactions in organic chemistry. chemistry. So which are the examples? What are the important examples of nucleophiles? What are the important examples of electrophiles? Taking nucleophiles, it should be negatively charged. Then only it can donate some electrons. And the second thing is, it can be a neutral species provided that it has some lone pair of electrons in higher energy molecular orbitals. It should have lone pairs, or it should have non-bonding. Okay, non-bonding electrons. Also, C double bond C. C double bond C, such kind of alkenes also, they are also good nucleophiles. And sigma bond can also act as a nucleophile, but it should associate with electropositive atoms, elements such as boron, silicon, lithium, LiCH3. I have this PDF, I will upload. Okay, LiCH3. Such a kind of sigma bond can also act as a nucleophile. Okay. So while coming to the electrophile, I already said that it should have lowest energy unoccupied molecular orbital so that it can accept the electrons. So if one accept the electrons, it should be positively charged. It should be positively charged. It can be neutral species, but it should have empty atomic orbitals. Then only it can accept, right? Then only there will be a flow of electrons from the filled orbitals to unfilled orbitals, right? So these are the main conditions. So in the case of electrophiles, also this HCl, because here there is an electronegative atom. So this is an electrophile. Br, that is an electrophile. Okay. So such kind of centers, sigma star and C double bond O functional group, they are pi star orbital. They have empty pi star orbitals. So C double bond O, they are the main electrophiles. That C, carbon C plus, electrophilic carbon in C double bond O. It's very important in organic chemistry. So the key point is that which is electrophile, which is nucleophile, and it is very easy to write whatever mechanism we want. And just we should understand the purpose of a particular reagent, what they will do. Then it is very easy. So I will just show some of the slides and we'll go to the next topic. Okay. See, as I told you that negatively charged species, neutral species, non-bonding lone pair of electrons. These are the best nucleophile. These are some examples. They can be bonding pi orbitals. They can be simple alkenes. They can be a sigma bond also. But it should be associated with boron, silicon, such kind of things, electropositive. These are the examples of some of the nucleophiles. And these are the examples for some of the electrophiles. So they have a low energy pi star orbital. So it is important that they should have a low energy unoccupied molecular orbitals. And also sigma star orbitals will also act as an electrophile if it is associated with the electronegative such as Br, Cl. And Br is also very weak. This Br bond is also very weak because here they are overlapping with 4s and 4p orbitals and their overlapping is very poor. When comparing with CC, it is not at all electrophilic. Just in the mind, we should have this in our, okay. So these are the examples for electrophiles, H plus, DF3, this C double bond O, HCl. These all are the examples for our electrophiles. Now we are coming to the first important thing in our clade. What is that? Nucleophilic addition to the carbon. So now we have an idea. We already have an idea that who is the nucleophile. So if I am, after explaining this nucleophile, electrophile, and all those things, if I am giving these reactions, your very clear to tell that this is the electrophilic center here and this Cn minus is the nucleophile. And I could say that this Cn minus, from Cn minus, this electron is moving to this particular center. So here new CC bond formation is happening. Now it is easy for me to this write this particular reaction, right? Earlier we will be thinking what is happening, what is where it will attack, whether Cn minus will go and attack here, whether it will go attack here. But now I am clearly know. Now I know that this is the particular center which is going to be attacked, and this is the particular person who is going to attack the center. So this is what important. This is why the basics is very important in organic chemistry. So here they are just explaining how the bonding is formed in a formaldehyde or formaldehyde. So in formaldehyde, there is an sp2, sp2. Here it is sp2 hybridized. This is also sp2 hybridized. So these sp2, sp2 orbitals are overlapped. Okay. And here other two orbitals are overlapped with hydrogen in the case of carbon, and in the case of oxygen, lone pairs are there. And this is the pi bonding in formaldehyde. CO pi bond made up of two p orbitals. So in C double bond O, when I'm saying about C double bond O, this pi bond is formed between two p orbitals. Okay. Now we are considering how this reaction is happening. So, this particular pi bond, I'm considering this particular pi bond. This polarization in the pi bond, it is skewed towards oxygen. This skewed towards oxygen means it is more electron negative, right? So the electron density will be more around this. Okay, and here I already told that lowest unoccupied molecular orbital is pi star. So this lowest unoccupied molecular orbital in this particular carbonyl functional group is skewed towards carbon. Electron density is skewed towards oxygen, but this pi star orbital, antibonding pi star orbital, is skewed into the opposite direction, and it has a larger coefficient at the carbon atom. Okay, so this is what happened. Now here what will happen? Here already this pi star is there, and HOMO, nucleophile is all filled orbital is there. So it will interact here and a new sigma bond will form. So here we know that here LUMO is a pi star orbital. So filling of this pi star orbital will cause the pi bond to break, and electrons from the pi bond end up as negative charge on oxygen. And after this, a proton will add to this negative center. This is what happening in a nucleophilic addition to carbonyl group. So here we understood what is a nucleophile, what is an electrophile, what is happening when a nucleophile is attacking to this particular carbonyl group, right? So these all things are involved in this. It is not merely just going and attacking. There is many things happening, and we should understand this, then only it will be very easy for us. Okay. So now it is very easy, right? Okay. Now moving towards this. So NaCN, H2O, HCl. Aldehyde. This is aldehyde. As I told you, this is our electrophilic center. We already explained. Cn minus is attacking here. This is the product. H plus is taken up by this particular negative group, and cyanohydrin is forming. Cyanohydrin is forming. So here HOMO is the sp orbital involved in the addition of cyanide. HOMO is the sp orbital, and LUMO is the pi star orbital. Now, another important thing is that how they are approaching. Whether this nucleophile is attacking perpendicularly, sorry, or it is attacking through a particular angle. What is happening actually? So it is really surprising that it is not attacking with perpendicular. Okay, and there is an angle of 107 degrees Celsius. That is the way it is attacking. And it is known as, I'm pronouncing it as Burgi-Dunit's trajectory. It's not that important for exam, but as a chemist, we should understand what it is, right? So nucleophile is not attacking like that. It's attacking at an angle of 107 degrees. And it is known as Burgi-Dunit's trajectory. So that what will happen? Maximum orbital overlap of HOMO with pi star. HOMO of the nucleophile with pi star of this, there will be maximum overlap and there will be minimum repulsion of the HOMO by the electron density in the carbonyl pi bond. In this, we know that there is an electron density and this is due to this oxygen center, right? So to minimize the repulsion between these, what is happening? It is attacking through this particular angle. This is how a nucleophile is attacking a carbonyl center. It is very important. Okay. Now coming to the another nucleophilic attack by hydride. So if I want this H minus to attack this particular cell, this reaction never happens. Nucleophilic attack by H minus never happens. Why it is so? Because if I want this H minus, I should take some NaH, and it has such a high charge density and it can only react as a base. Here this H minus will always react as a base. It should be in your mind. So what I will do? I can take BH4 minus. I can take what? BH4 minus. And here the reaction will happen like this. And it's a very, very useful reactions to form what? Alcohol, right? It's very useful reaction to form alcohols. So the hydrogen atom, here what is happening? The hydrogen atom together with the pair of electrons from BH bond will be transferred to the carbon atom of the CO group. This is what is happening here. Okay. And when I am using NaBH4 with H2, this particular center is reducing and this is the product. Here also, when I am using, this is happening. So NaBH4 is a good reducing agent. So here we could see that water is there. Here there is a presence of alcohol. So the water or alcohol solvent provide the proton needed to form the alcohol from the alkoxide ion. So here we could see that what is forming first? An alkoxide ion. From this alkoxide ion, it's protonating. So the proton, that particular proton needed to form the alcohol is provided by this water or this solvent such as alcohol. That is what is happening in the nucleophilic condition. I think it's very clear. So here we are discussing about the sodium borohydride. This is sodium borohydride. But the sodium borohydride is a weaker hydride than this. It's a weaker hydride than this, and it can be used with water also. But if I am using instead of this lithium aluminum hydride, LiAlH4, what is instead of this, if I am using LiAlH4, it is a powerful hydride donors than NaBH4 and it will react violently with water. So sodium borohydride will react with both the aldehydes and ketones, but the problem is that it is not that reactive with less reactive carbonyl. Here we could see that here there is an aldehyde group and here we can see that here there is an ester group. So it is only reducing this particular group. And here also it is only reducing this particular. And here also it is not at all considering this halide, right? So this is what happened. So it's a very weaker hydride donor and less reactive species, it is not that reactive. Okay. Now consider addition of organometallic reagent. So here, when I am saying MELI, So I knew that MELI is a nucleophile. Why MELI is a nucleophile? We already told that sigma bond can be a nucleophile if it is attached with this electropositive elements such as lithium, boron, silicon. So this is the nucleophile here, and this is the electrophile here. So that I can easily write here in MELI. In this, when I'm considering this bond, this is highly polarized towards carbon, right? This is highly polarized towards carbon because this is more electropositive than carbon. So this is highly polarized towards this particular thing. And this will attack, and what will happen? Hydrogen will be taken up by this alkoxide. Same thing happens here also. And here HOMO will be the LIC sigma to polarized towards C. HOMO. Here LUMO will be the pi star, as we already discussed. And here one of the most important things we have to be considered that when I was saying earlier reaction, there was no one. They were not specifically mentioned 1 and 2. But here they specifically maintained 1 and 2. Why? Because here when I am taking MELI, it will react violently with water. So in the first step, we will give MELI. In the second step only, we will react this with water. Okay, so we should careful about while using in lab also, organolithiums are very, very dangerous. It should be should always keep in low temperature. Okay. Same reaction will happen with the what? The other kind of like Grignard reagent. The same reaction. This is what the most important nucleophilic additions. Now you got an idea how to approach the organic chemistry. Right? So here we discussed some of the important reactions, right? So now you should be able to understand like what is attacking, from where to where, how they are attacking, how the interaction is happening. So it's very easy if we are studying like this. We are approaching organic chemistry like this. It's very easy to understand organic chemistry, and it is very easy to write any of the mechanism. Okay, so this series will continue, and please comment what all topics you want. I will start another series on inorganic chemistry and physical chemistry. The reference will be Atkins and Suchi. So in this particular organic chemistry series, I'm taking Claydon as reference so that after completing the series, you will be thorough with the basics of organic chemistry. So if you are liking this classes I'm taking, please subscribe, like, comment what you want and what all changes you are expecting from me, all those things. And I also know that today exams were there, CSIR exams, that discussions will come soon in our channel. And all the very best wishes. So you can always mail to me like the cubicoworld@gmail.com. I will be available. So that's all. Thank you all. Bye.